A quick recap. We loaded in the data using a slightly tricky method, but actually once you get used to it, it's very flexible. You can load in any data. We detrended the data. We calculated the tide simply by, because we already had a surge, we didn't need to do a harmonic analysis. We could just subtract that to get the tide, because the tide plus surge is the water level. Clearly the BADC have already done a tidal analysis, that's why it's in there. And then we got the data into this nice formatted timetable where we have the time, water level, detrended water level, tide and surge. Now the reason why we use timetables is it's just really handy to plot the data. Okay, so we're going to create a new figure, but this time, again, I'm just going to cut and paste code from previous practicals just to make it much easier. So let's just get a previous figure. Again, notice I put the units normalized and the position to make the figure nice and big. Now this time what's really nice is rather than having to do tiles or anything, and rather than having to have lots of different axis labels, we can just use stack plot TT. And we can run that. And all in one go, that basically produces a plot for us automatically with the names of the variables and everything. So there you can see we have a nice stack plot. So we've got the water level, the detrended water level, the tide and surge. Now what I'm going to do is I've saved this as S, and now I can select various properties. So I can do line properties. The first one, I can set the color. So this will be the top one as blue. And then I can copy that again, copy it 4 times. So I'm going to do the second one, third one, fourth one. So I'm going to do blue, black, black. I always try and have blue, black is a K. Always try and have tides as red, surges as green. I always try and be consistent with whatever I do. And then finally, I'm just going to set the font size. Oh, sorry, I've done this in the wrong box. Let's just do it in the correct box. Jumping ahead, and then I'm just going to set S's font size as 14. So here you can see it's a nice way. It's a lot easier. It's just one line of code really, with some additional to plot that. Probably nice to plot the scales a bit better here. Don't know why it's going all the way down to -3. That's a bit odd. Okay, now we're going to extract the annual maximum water levels, because remember from the lecture, that is what we need. So I'm going to have a variable called TTAM for annual maximum, and now what's really nice is we can just use this retime function. Previously I'd have to do a loop and some complicated code, so I'm going to do a retime on TT. And first of all, you can do the help menu to work out what it was, but first of all I'm going to do a yearly and max. And basically what this is going to do is it's going to go through, and now it just tells me the maximum each year. So the maximum in 1991, maximum in 1992, maximum in 1993, all the way on. So I've just got a maximum water level, maximum detrended water level, maximum tide, maximum surge. So you can see actually the largest surge was 1.2 meters in 2014. That was a very big 14th of Valentine's. I remember that storm very well. You could change this to min, you could change this to monthly. It's very flexible, so I encourage you to look up the help T-time, but it's a really fantastic function. You can do lots of really good things in it quite simply. So you can go down here and it tells you what, so you can have the sum, the mean, the median, you can have different seconds, quarterly, so it's very flexible. Okay, and then what I'm going to do is bring up a new figure. Again, we can just borrow the code from here. Bring up a new figure. I'm going to do the stack plot, but this time I'm only interested in the water level. We're going to do the stacks on the water level. So I'm going to stack this time the AM, but I'm only going to stack, we need this columns 1 and 2, which is the detrended data. So this just gives me the annual maximum values. Okay, so this is the annual maximum values. And you see the detrended, it should be higher because we take away the trend relative, and 2019 should be identical, which it is. So those are the annual maximum values. Okay, so now I can do my fit. So what I'm going to do is create a variable called RP. It's going to be numbers, and I'm just going to have these numbers here. So these are what I want to calculate my return periods on: half a year, 1 year, 2, 5, 10, 25, 50. Take away the and there, 1,000. Okay, so here I'm just setting up a variable. And what I need to do now is convert this into a probability. And I can do that using this code here. It's a bit confusing to explain this, but essentially it's just 1 over the return period, really, minus 1, so that this is now a return period. So 1,000 years has a probability of 0.0001, similar to what we talked about when in the coast flooding lecture. Okay, now we can do a fit distribution. So I'm going to get the parameters, and we're going to start with a very simple one, the gumball, which is the straight line. So I'm going to do a fit distribution. Now gumball, for some reason it's minimum. I don't know why they've chosen that, so we need to make it negative. And we're going to put column 2, which is the detrended data, and it's TM, the detrended annual maximum. And the type of distribution is a gumball, which is just an EV distribution. Now this, as you saw in the what have I done wrong? Oh, it needs to be dot 2, sorry. The second column. So here we've got 2 parameters, a mu and a sigma, so it's a straight line. So the slope of the curve and the sort of essentially, but these are, and again in the lecture notes I went over these 2 parameters. Okay, now what I need to do is, now I need to do the inverse to get the return period. So I say R level gum is the EV inverse, and I give it my probability P. So I want to calculate these at probability P, and now I need to do my, so I'm going to be par gum, and the first one that you need to enter is the mu, and then par gum, the sigma. Okay, now what I want to do is, because it's minimum, because I made it a negative here, I need to times this by -1 to get it to a maximum. It's a bit confusing. I don't know why MATLAB have chosen to do that. But now we've calculated our return period. So these are our return period, the RL gum. So the 1 in half a year is 5 meter. The 1 in 1,000, or 1 in, was it 1,000, or yeah, 1 in 10,000 is 6.4 meters. So a flood, if the water level was to reach 6.4 meters, that would have a very low probability of occurrence, 1 in 10,000 year return period. Okay, so now we can do a figure. I'm just going to nick code from here again. So let's bring up a new figure, and then we're going to do next tile. I am going to do a 1x1 figure to start with. And what ideally, well, I'll do the plot to start with, but I'll show you, I don't do this. So I'm going to plot my return period against my return level gumball, and I'm going to set that as red. I'm going to add a X label, return period. The return period is in years. And I'm going to add a Y label to say return level in meters. I'm going to do a title, a gumball fit. Now let's run that. Now plotting things in an ordinary plot gives you this very weird stretched curve, and so it's much better to plot it on using a semi-log x. So basically we turn the x to be a log, and then you can see it's a straight line. Now I'm just going to nick the code again to make the text size 14. But what I'm going to do is some other things as well. So let's set the x lim. Let's set the x ticks and I'm going to choose where I want chicks. I'm going to have 1, 10, 100 and 1,000. Now let's set the X tick. Now normally what it does it to the power of 10, but I actually want it written out. So I'm going to have 1, 10, 100 and 1,000. I'm going to, as always, put a box on, put my grid on, and run that. X tick labels, spelled that wrong. X tick labels. Oh, this needs to be 1,000, so you can't have two numbers the same. Okay, so there you have your straight line. So you can see a 1 in 10 year event is about 5.6 meters, 1 in 100 is about 5.9, a 1 in 1,000 is 6.2, 1 in 10,000 is kind of 6.4. Most flood protection is 1 in 200 years. So it sort of says if sea level gets beyond a 6 meter at Portsmouth, you're going to have some quite severe flooding. Okay, so what we are going to do next is test, is this a good fit? Does this actually fit the data? And to do that, we're going to use a very simple sort of empirical method. So first of all, I'm going to find the length. So I'm just going to find the length of TTAM dot column 2. So that will really be the number of years. So it's 32 years. And then what I'm going to do is my empirical model, my P empirical. You should have seen this in the notes, but I'm going to go from 1 to LE, and then I'm going to divide that by LE plus 1, just so that the last one is always 0. And then what I'm going to do is my plotting positions. The first row of the plotting positions is going to be the inverse of that. So it's -1 divided by log PEM. This is the kind of inverse of, essentially the inverse of this. We're going from a, we're working backwards now. We're going from a probability to a return period. And then the second column of the data, this will make a bit more sense when I plot it, is we're going to sort the data into order of size. So basically what you're saying is the largest value has a probability of 1 divided by the length of data, so 1 over 32. The second one is 2 over, well, because you add 1, it's 33. So it's just a kind of simple way. And then what we can do is we can put that, we can do a hold on to add it to the plot, and we do semi-log x. We're going to plot PP shift column 1, PP column 2. So this is just a simple, we're going to do this as black circles. I'm going to change the marker size to being 10 and the marker face color to being red. Okay, I've made a mistake here. I think I just needed to divide it by. So instead of missing an operator, I needed equals. Sorry, I'm going too fast, but you can see that doesn't matter. You know, if there's errors, you'll get a red thing. If you read it, you know, over experience. And I'm actually going to plot those as black rather than red. Okay, so now you can see the data. So those 32 annual maximum, you can see that this curve is fitting through them, but it doesn't, a straight line doesn't fit very well towards the end. And actually the curve kind of flattens off a bit. So probably I'm overestimating this really here. I probably shouldn't be doing this. So it's probably better to do a GEV fit, which has 3 parameters. So again, so I'm going to do the parameters of a GB. I'm going to fit a distribution. Again, we do the negative, because for some reason I'm fitting it to D, but this time rather than doing a Gumbel, an EV fit, we're going to do a GV fit. And this time you'll see it has 3 parameters, and one of them allows that curve to kind of shape off. So now we have a K, which is a shape. So if it's negative, we get the curve bending down, and then we have sigma and mu. Okay, now what we can do is use the return level of the GV is now use the inverse function. So GV inverse, we give it the P like we did before, but now we have to give it the 3 parameters rather than 2. So we have the par GEV K, par GV sigma par GV mu. You can see I've done the spelling here. Okay, so this should give us the return periods. GEV unrecognized function. I obviously spelt that wrong. Oh, it should be I had in rather than inverse. So you can see I could just click on fix it. It's very, very nice. You never used to be able to do that in MATLAB. That's a new thing. And then because this is designed for minimums, I've got to times it by 1 to get to our maximum. Okay, now I'm going to cut and paste this code. To plot the GV. So rather than the gumball here, I'm going to plot the GV, and I'm also going to plot the plotting positions. I don't need to calculate this again because it's exactly the same data set. So I just need to hold on, plot that. And I'm going to plot this one as blue instead of red, so you can kind of see there. And this one you can see it now bends off, and I think it does fit the data slightly better. You never get a perfect fit because these are very rare values, but you can see it fits the data a little bit better.